In this video, I will talk about the variational iteration method for Volterra Integro-Differential Equation. Volterra Integro-Differential Equation is that differential equation in which the derivative and integration appears together. So the standard form of Volterra Integro-Differential Equation is 0 to x k1 xt u of t dt plus 0 to x k2 xt u nth derivative dt is equal to f of x, where k2 xt is not equal to 0. So this is the Volterra Integro-Differential Equation. Here k1 is the kernel number 1, you may say, for this integration, and this is kernel number 2 for second integration. Here n is the nth derivative. So what we do, we want to convert this equation 1 into ordinary differential equation. Okay, but first what we do, we differentiate this equation 1. So we differentiating above with respect to x, d by dx 0 to x k1 xt u of t dt plus d by dx 0 to x k2 xt un nth derivative dt is equal to d by dx f of x. So in the next step, we apply Leibniz rule. Leibniz rule says that take a derivative of upper limit dx by dx, then put that upper limit in the integrand, this whole value. So we get k1 x u of x. Then we apply the lower limit. Since the lower limit is constant, we get 0 minus d0 by dx. So no need to write it over here. Then we have plus. Then we have to take derivative of integrand 0 to x partial by partial x k1 xt u of t dt. So here we have solved the first term on the left hand side. We actually took a derivative of left hand side. Now the second term will become again the upper limit. First the upper limit dx by dx k2 x nth power of u. Then the lower limit is 0 plus 0 to x partial by partial x and k2 xt u of n t dt is equal to f dash x. Okay, since we want to convert equation 1 into the ordinary differential equation, for that purpose we needed u nth separately. So what we do, this will become 1 and we divide this whole equation with k2xx. So we get k1 xx divided by k2 xx u of x plus 1 over k2 xx 0 to x partial k1 by partial x u of t dt plus, and here we get u of nth derivative, u nth derivative, function of x plus 0 to x partial k2 by partial x, nth derivative, function of t dt. So here you can see that we have separated nth derivative. There is a reason for that. We will learn about that. So we keep this term over here and all the terms, these all terms will have some function. What I should also write, the right hand side is f dash x. Okay, I rewrite it as u nth derivative function of x, right hand side, or maybe I should write it like this, plus 1 over k2 xx 0 to x partial k1 by partial x u of t dt plus k1 x divided by k2 x u of x plus 0 to x partial k2 by partial x u nth derivative dt minus f dash x is equal to 0. So here we have u nth derivative x plus this whole term, this complete expression on the left hand side becomes a function of u, u dash, and up to, since there is nth derivative as well, so this becomes nth derivative. After integrating it, after integrating this term, what is our function, we can generally write it as a function of x, u, u dash, u double dash up to u nth derivative, which is equal to 0. So we have successfully converted equation 1 into the ordinary differential equation. It is not actually ordinary differential equation, but in fact this is integro-differential equation. The reason is, if this in this equation u is unknown, which is a solution, and u also appears over here and u also appear over here, so it means that we cannot solve this integration until we have a solution. So it means that this is integro-differential equation. This is integro-differential equation, ordinary differential equation. Okay, and we learned that in the previous video, when our differential equation is look like this, for example, if it is first order differential equation d by dx, something like that, then we have lambda is equal to -1. So our linear operator will be this nth derivative over here. Here this n is the approximation which shows that the iterative solution. Similarly, if we have, for example, dun by second derivative, if we have second derivative, then that lambda was, as you remember, it was xi minus x. Now, if we have nth derivative, for example, if we have nth approximation and the nth derivative of that approximation, then we can write dnun by dxn. Okay, so we generalize the formula for lambda. Then the lambda will be -1 n 1 over n minus 1 factorial and t minus x n minus 1. Remember that here we are working with t. Previously we were working on xi, so that's why we had xi over here. So it depends what is your integration. So here I have put a t over here. The reason is there is a t, but you can in fact generalize it for xi as well. For example, when I put n is equal to 0, n is equal to 1, I'm sorry. So it means that we had first order differential equation, first order integro-differential equation or simple differential equation like this. Then we have lambda is equal to -1, 1 over 1 minus 1 is 0 factorial. Then we have t minus x, 1 minus 1 is 0. So finally you get -1. And here it is -1. Similarly, when we have n is equal to 2, then we have lambda is equal to -1 square. 1 over 2 minus 1 is 1 factorial. T minus x is 2 minus 1, 1. So we get t minus xi, or it depends. Either we have xi, then it becomes xi minus x. So similarly, we can find third derivative, lambda for third derivative, so on. So that's the general formula that we have to discuss, or we have to use for the integro-differential equation. Okay. So this is the theory of converting our problem into integro-differential equation, then solving that integro-differential equation with variational iteration method. Okay, so I'll solve this some problem integro-differential equation with the variational iteration method in the next video. Thank you for watching.